15.4 Segment relationships in circles, geometry. So the essential question, what are the relationships between the segments in circles? We've learned about chords, we've learned about tangent lines. We're also going to be talking about secant lines, okay? And basically, in order to figure out the relationships between them, we're going to be basically using three different theorems, okay? So especially with chords. So we have chord product theorem, we have secant product theorem, and we have secant tangent product theorem. And this reveals everything you need to know about secant lines, tangent lines, chords that are basing themselves around a circle. Okay, so this is very theorem heavy, so make sure you understand the three theorems for this subject, and you should be just fine. Okay, so make sure you know how to identify when to use them too. Okay, that's the big one. All right, so first off, we have chord product theorem. So if two chords intersect inside a circle, then the products of the lengths of the segments of the circle are equal. So notice how I already highlighted. Basically, AE times EB is going to equal basically ED times CE. Two different chords, but if you multiply those two segments together, from each chord, you're going to realize they are equal to each other. Okay, and that's always, okay, especially when they're chords. Okay, and you're probably like, why? How is that possible? Well, both, remember, chords exist from the inscribed or the edges of a circle in the first place, so they have that in common. So it's not surprising that they have some relationships. Okay, so let's see an example. Okay, so we're going to have, let's see, CE, okay, this big, huge segment, part of the chord, okay, times ED, okay, and then we're going to have AE, which is the longer side of this. The image is a little warped. I think your photo is a little bit better on this, but my image is a little warped. And then that's going to be multiplied to BE. So let's try this out. Let's actually do some math. So according to the chord product theorem, we should have CE times ED equaling AE times EB. So let's try it out. Again, we're using the chord product theorem to find x. X did not give it to us. Okay. All right. So CE is 6, and that was a terrible 6. ED was 2. AE is x, and EB was 3. So we have 12 equals 3x. How do we get rid of a multiplying 3? We divide, division property, and we find out that x equals, well, what's 12 divided by 3? Boom. All right. So x equals 4. And that's just another example of your homework. And I think even your tests will talk about this. All right, let's look at example 2. So in example 2, all right, we're going to find x again. So let's see, where to start? We have, let's see, HG, all right, times GJ, and then we have KG times GI. So let's try this setup. Again, I'm setting it up this way. Now remember, multiplication is associative, so what's 2 times 3? What's 3 times 2? They're the same thing, so don't worry about the order, just make sure they belong to the same chord. And as I set it up, I'm just showing you, okay, This equals, let's see, we have kg times gi. So let's go ahead and substitute. Hg was 9. Gj was 8. And kg was 6. And gi, we don't know, it was x. Okay, 9 times 8 is 72. And then 6x is just 6x, but we have to get rid of a multiplying 6. So we divide, use the division property, and x should be equaling 12. All right, so notice how I'm just getting a product from each chord, and I'm setting them equal to each chord. Okay, so this chord equals this chord, so this part times this part equals this part times this part. Okay, that's basically what the chord theorem is. So example 3, that's on you. Try it. Okay, figure out what chord is what, and what segment times what segment, equaling the other chord, what segment times what segment. Okay, I'm going to check you guys for this when I get back, all right, on Friday. So good luck. All right, next thing we have is the secant product theorem. So a secant, it's a part of your definition, is a line that intersects a circle at exactly 2 points. So as you can see, 1, 2, 1, 2. So it's not like a tangent where it only crosses once. This is a secant. It'll go through at least twice. Okay. Now a secant segment is a part of that line. So a secant segment is a part of the secant line with at least 1 point on the circle. So here's, there's a secant segment right there. Okay. In fact, this is actually a secant segment. We have a more specific term, I believe, for what BE is, and that's going to be an external secant segment. Basically, they're on the outside. Okay. Sorry, that whole Stain song just comes in my head. 'Cause I'm on the outside, I'm looking in, I see a secant. No, all right. But secant segment, external secant segment is the guy on the outside. Okay, so secant product theorem. If two secants intersect with the exterior of the circle, then the product of the lengths of the secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. So basically, we have a situation where AE, this whole guy, all right, times BE, the outer guy, will equal whatever CE is, this whole long guy, times the exterior secant. Okay, so this whole secant line times the external secant segment will equal this whole secant line times his external secant segment. Okay, so let's go ahead and see an example of this. All right, so example 4. As you can see, we have two secant lines, and we basically have to figure out what x is, knowing this. So here we go. All right, first things first, AC is a secant line times his external, and his external is what? AB. And we're going to set that equal to the other guy. So the other secant line is going to be AE times his external line, which is AD. Okay, and let me get a little bit more color coded here. So AC, okay, then we have AE, the whole guy. Okay, so let me, all right, sorry about that. Kid knocked on the door, so I had to go see what that was. All right, so now let's color code. AC was being multiplied by his exterior, which was AB. and then AE was being multiplied by his exterior, which was AD. Okay, it always has that pattern when you have two secant lines. Okay, so let's go ahead and substitute. AC was 5 plus x, right? Right, AC, 5 and the x, so 5 plus x. AB was just a simple little 5. AE, okay, AE is 6 plus 6, isn't it? So that's a total distance of 12. And his exterior angle, or a segment, exterior secant segment was 6. Say that 10 times fast. All right, let's go ahead and distribute. We got 5x. Wow. Plus 25, and that equals 72. Go ahead and use the subtraction property. And now you're going to have 5x equaling, and somebody's knocking again, so okay, so that's the second time someone has bothered me. Alright, so where were we? Let's see. Alright, so here I was doing this. Alright, so right, so we have 5x equals 47. We'll use the division property. Our answer is not going to be pretty, I can tell you that already, because that fraction, I got a 7 there. You know. So you're going to have x equaling 9.4, which it happens. You never get perfect answers sometimes, all right? It happens. All right, so let's go ahead and burn and churn. So next problem. So example 5. Again, I want to be thinking, all right, here's my secant, SP, times, and let's see, and we're going to have the other secant line too. So you're going to have SP times, who's his outer guy? RP, or PR, okay? Okay, his outer secant, equaling the other secant line, which is PU, and it doesn't smell, times his exterior secant, which is PT. Let's go ahead and start substituting. SP is 8 plus 6, which is 14. Okay, because 8 plus 6, all right, equals 14, times PR, which is 6. It's a terrible multiplication sign, I know. PU is going to be x plus 7. Okay, x plus 7 times PT, which is 7. So we're going to go ahead and get 84 on the left, equaling 7x plus 49. We'll use the subtraction property to get rid of that 49. And you're going to get 7x equals 35. Use the division property one more time. And you're going to get x equals 5. Dunsies. All right. So again, I just took the entire secant line times his exterior segment, equaling the other secant line times his exterior. And then you can solve. So number 6, example 6, that's on you. Good luck. All right, last thing we need to talk about is the secant tangent product theorem. So with this guy, okay, you need to know that a tangent segment, what that is. So let's talk about it as quickly as I humanly can because the bell's going to ring in like 10 minutes. All right, so part of your definitions again. A tangent segment is a segment of a tangent line with exactly one endpoint on the circle. So here's a tangent segment, okay? He's kind of like an exterior segment, isn't he? So he's on the outside looking in, okay? All right, so let's see. The secant tangent product theorem is when you have a secant line like AC and a tangent line like CD. If you have two of those, you're going to be using secant tangent. So you have to identify, what do you have? Do you have two tangents? Do you have two secants? Do you have a secant and a tangent? You know, what do you have? Chords? What do you have? Okay, so you have to identify what situation's which. So now example 7. All right, we have our tangent, okay, and let me look back. Did I skip the math on this one? Yes, I did. Shame on me. All right, so basically all you need to know is you take the full secant line, which is AC, okay, times his exterior angle, which is BC, and that's going to equal to your tangent line squared, always, okay? So let's go ahead and look at the example. So you have let's see, BD is our secant, so BD, and we're going to use the secant tangent theorem, so we're going to have BD times BC equaling AB, our tangent segment, okay, squared. So let's go ahead and solve. So BD is going to be x plus 2, right, because that makes the whole secant line, times BC, which is exterior, okay, which is 2, equaling AB, which is 5 squared, okay, because remember we square the tangent. Let's distribute. We have 2x plus 4 equals 25. Go ahead and use a subtraction property. We'll use algebra to figure out the rest. 2x equals 21. Use division property. We're going to get a decimal answer, probably a 0.5. Yeah, so x equals 10.5. So that's how we can use the secant tangent. So example 8, I'm burning and churning because I'm running out of time. So we're going to take the whole secant line, AC, times his exterior secant, which is BC, equaling our tangent, and our tangent is definitely CD. And don't forget, if we're using secant tangent product theorem, we're going to square our tangent, okay? So AC is 6 plus 4, right? So that's 10. BC is 4. CD is just x squared. And we're going to get 40 equaling x squared. How can we get rid of a square? That's right, we have to square root. So once you square root with this guy, you can always use the factoring tree to figure this one out. But you should get x equals plus or minus, but since we're talking about distance, it's going to be 2 times the square root of 10. And if you're looking for an approximate answer, because you're probably using your calculator, you'll get 6.32. Not every answer is going to be beautiful, but it's an answer nonetheless. All right, so example 9, that's on you. And again, I'm going to double check you guys' work because I care. So I'll see you guys mañana. Your homework, page 823 through 825, numbers 5 through 8, and 10 through 15. The problems I assigned are very much like the examples I just gave you. If you have any questions, I am tutoring later on today. So good luck.